Here are the solutions to homework set number 12 for ECE 341. In this homework set, we're looking at t-tests with a single population. The first problem is earlier, back in homework set number 2, we wrote programs for calculating the odds of being dealt 2 pair when being dealt 6 cards, or 6-card stud. We calculated the odds as 12.44%. Can I check that with the Monte Carlo simulation? We also wrote a Monte Carlo simulation where you're dealt 6 cards and it determines what kind of hand you have. If I ran that 4 times, this is the number of times they got 2 pair in 100,000 hands. From that, what are the actual odds of getting 2 pair? Now this is a population problem, so I want to know the population's average. So there I divide by the square root of n. For an individual, like if I ran this the 5th time, I would not divide by the square root of n. So anyway, the procedure is given your data, find the mean, find the standard deviation. The t-score comes from a t-table. I have sample size of 4, meaning 3 degrees of freedom. I want 5% tails, so the t-score is 2.35. I'll go left and right, 2.35 standard deviations, and again, this is for a population, so I divide by the square root of n. And it says the population's average is somewhere between 12,408 and 12,565. If I plot that, this is the PDF for the Monte Carlo simulation. I get the number of hands that I get that are 2 pair varies over this range. 90% of the time, the population's average has this PDF. So here, this is your x bar, and the standard deviation is going to be s divided by square root of 2, or square root of 4, sample size is 4. Gives you this PDF. The 90% confidence interval is between the red lines, and the actual odds are the blue line. And notice that I don't know precisely what the actual odds are based upon the Monte Carlo simulation, but I can bracket it. It's somewhere between the 2 red lines, and that checks out. The actual odds are in that range. So that was with 4 hands. Suppose instead I ran the Monte Carlo simulation 20 times. I'd get 20 data points. It has a mean, standard deviation. With 20 points, I now look at 19 degrees of freedom, 5% tails. And notice, I get a better idea of what the actual probability is for 2 reasons. First, the t-score got smaller. That reduces my spread. In addition, since I'm talking about populations, I want to know what the overall average is. I divide by the square root of the sample size. This reduces the standard deviation as well. So when you do that, I now have a better idea of what the actual probability is, actual odds are. It's somewhere between 12,389 and 12,460 out of 100,000 hands. And what that looks like on the same scale is my distribution has tightened up. Again, this goes down as s over square root of n. As n gets bigger, this gets tighter and tighter. My 90% confidence interval are the red lines, and the actual odds are the blue line. If I want to know precisely what the odds are, I need to let the sample size go to infinity. Then I would know precisely. In general, with a t-test, I can't tell you precisely what the odds are, but I can give you a bracket. It's somewhere in this range with a probability of 0.9. Problem number 3. Same thing with 6-card draw. Now, 6-card draw, this is a pretty complicated derivation. To get 4 of a kind in 6-card draw poker, I'm dealt 6 cards. If I have 4 of a kind, I keep them. If I have 3 of a kind, I discard 3 cards, draw 3 new, trying to get 4 of a kind. And doing that, or various combinations of what I have, doing that, I computed the odds as being 0.00682, or I should get 682.87 4 of a kinds for every 100,000 hands. Well, let's try it. Run the Monte Carlo simulation 100,000 times, and here's what I get. With that, I've got a mean, I've got a standard deviation. This again is a population question, so the spread will be the mean plus or minus 2.35 times the standard deviation divided by the square root of the sample size. Again, this is for a population. I want to know the overall average, this number. Gives me, I'm 90% certain it's between 711 and 772. What that looks like, this is the PDF for the actual odds of getting 4 of a kind in 6-card draw. Here's my 90% confidence interval. And the actual odds, I should say actually calculated odds, are right here. This kind of tells me there's something amiss. I'm 90% certain that the Monte Carlo is inconsistent with my calculations. My calculations are off, or the Monte Carlo simulation is off. One of the two are wrong. 90% certain. That's with a sample size of 4. Let's repeat with a sample size of 20. Run the Monte Carlo simulation 20 times. It has a mean, standard deviation. When I do that, I tighten up the band because the t-score gets smaller. In addition, I divide by square root of n. N gets bigger, so this gets smaller. Put it all together, I've got a tighter bracket for where the actual odds are, between 765 and 749. So same scale as before. The standard deviation got smaller, t got smaller, so this tightened up. I'm now 90% certain that the odds are somewhere in this range. Here's the calculated odds. So again, it tells me that either the calculations are wrong or my Monte Carlo simulation is wrong. The two are not consistent. Problem 5. Go to humanbenchmark.com. There you can take a test. A red screen comes on, you wait for it to turn green. When it does, you click the button, and it measures your reaction time. Now I did that. Here's my reaction time for 5 trials. It has a mean, standard deviation. If I want to know, if I ran the experiment one more time, say number 6, where is that data going to lie? That's an individual. For individuals, I do not divide by square root of n. So I've got sample size of 5. I need to go to a t-table, 4 degrees of freedom, which would be, here's my t-table, with sample size of 5, 4 degrees of freedom. 2.13 is 5% tails. Okay, where were we? There we are. Okay, so we'll go left and right, 2.13 standard deviations. It says the next time I run the experiment, my reaction time should be somewhere between 221 and 373, with a probability of 0.9. And that kind of makes sense. Looking at your data, the data lies between 221 and 373, so that's reasonable. And that's what it looks like as the PDF for my reaction time. Problem number 7 says, well, what's the chance that the next time I run the experiment, I'll have a reaction time less than 200 milliseconds? Well, to determine that, I take the distance from 200 milliseconds from the mean. That's my t-score. That's going to be your mean minus 200 over the standard deviation. That comes up with a t-score of 2.74. Using a t-table with 4 degrees of freedom, I can convert that to a probability. This is 2.5%. A different question is, what's my overall reaction time? Is my overall reaction time less than 200 milliseconds? Now that's a population question. So in that case, I divide the standard deviation by the square root of the sample size. I now want to know how far is 200 from the mean. So now my t-score is going to be your x minus 200 over s, but in this case, I divide by the square root of the sample size. So now my t-score is 6.13. This area is 0.03%. So there is a chance that my overall reaction time is less than 200. It's not real likely. So that is homework set number 12 for ECE 341.